Right, so this is the first lecture on one of the first main things that we will be studying in linear algebra, and we begin with linear systems of equations. To start with, first of all, let's analyze the this heading. Let's look at the word linear, first of all. So what we're going to be dealing with are linear equations. So linear equations, as opposed to nonlinear equations, are equations where the variables occur. First of all, we're going to be looking at more than one variable. So there's going to be more than one unknown. And for instance, as an example, if you look at this equation, this is a linear equation, as opposed to this equation, okay, which is a nonlinear equation because of the presence of this square. So linear, when we talk about linear equations, we're talking about where we're talking about those types of equations where the unknowns only occur as they are. The slight variation that is allowed is that they're multiplied by constants. So for instance, 3x plus y is still a linear equation, but x squared plus y is not a linear equation. So if I were to draw a line here and say linear, for instance, 5x plus 2y minus 3z equals 6 is still a linear equation. It's got three unknowns, 1, 2, and 3. However, this equation, x plus sine y equals e to the z, is a nonlinear equation. So these are nonlinear equations. Now I'm only presenting these so that you can see the contrast between the two ideas, two major ideas, in fact, both extremely important. Nonlinear equations is a humongous topic in itself. This particular course on linear algebra is, of course, going to be dealing with linear equations only. So here, my intention is simply to get you to quickly understand what we're talking about. Now, the word linear, of course, it means like a line, all right? Linear. So it's like a line, comes from the word line. Now, if you look at the first equation, this one, okay, I can rewrite that as y equals minus 3x plus 2. So that is essentially, so that goes through the point 2, okay, its intercept is 2 here. And so basically this line here is approximately looking like this. The point is, it's a line. It's a straight line with the slope, negative slope minus 3 and y-intercept 2. You could draw that. Or you could draw planes and so on and so forth. But they cannot be squared, no square roots, no cubes, no sines, cosines, tans, none of the transcendentals. So that's the term linear here that you see. Now let's look at what do we mean by systems of equations. So let me write something down that you might be familiar with. So let's look at this. X plus 2y equals 3. X minus 2y equals 5. So if you look at this, these are, you'd see something familiar here, simultaneous equations. Okay, and you would know how to solve these. There are two ways to solve this. You can use a substitution, whereby you can say, well, x is equal to 3 minus 2y, substitute it into the other equation, and it gives you y is equal to minus a half, and so x is equal to, it turns out to be x is equal to 4. Okay, now that's one way, and the other much more popular way, I think, more people do it this way, is just cancel these two. So this is going to be 2x equals 8, x equals 4, which implies y is substituted back into any one of the equations is equal to minus a half. Right? So you end up with a solution which is that x is equal to 4 and y is equal to minus half. So this is well known, a well understood idea of solving simultaneous equations. Now in school you would have gone up to 3 unknowns in three equations. Okay. Now what I want you to think about is here these simultaneous equations and solving them. These simultaneous equations are a system of equations. okay, form a system of equations. Our objective is going to be looking at not just 2 by 2, two unknowns and two equations, or three unknowns and three equations, but rather n unknowns and m equations. So we want to look at umpteen equations with lots and lots of unknowns. And of course, our objective is going to be to try to use a computer to solve this. So a linear systems of equations are basically, you have a certain number of unknowns and a certain number of equations, and our objective is to solve those systems of equations. So let's look at how some notation and some ideas about how we can represent when I'm saying large number of unknowns and a large number of equations. Clearly, this x, y, z, and a, b, c being for letters representing the unknowns is not sufficient. There's only 26 letters. A good efficient way to represent equations is basically to use the subscript 1 and a counter subscript. So what I mean by that is x1 plus x2 plus x3 plus up to, say, xn. So that means we have n unknowns. So we have n unknowns. Okay? N unknowns. So we have n unknowns. Now, on the other hand, if we now obviously, as I said, these are fine. These are n unknowns. But should I, for instance, here, what would be appropriate is to have, of course, coefficients. And one could think of this as being a1, a2, okay, a3, an, okay, would be a good idea. However, if you think about it, that's fair enough. That's fine. That's one equation, and of course it's got to have a right-hand side. So let's say that's b1 on the other side. Okay, but here's my question. If I use this a1, a2, a3, an, what about the second equation? Because one equation is not sufficient, really, right? We said n equations and, of course, perhaps n or m unknown, n equations and n unknowns. We have the n unknowns. What about the m equations? So if I can't rewrite a1 because I need to have different coefficients. So what is better is to use a double subscript here to indicate that this is the first row, the first equation. So the first letter, the first number here is represents the equation number in a way. So these are all equation number 1 up to equation number 1. All of these equation number 1, and we have therefore now these n coefficients. Now in the second equation, of course, these x's will not change, but here the coefficient now, because it's the second equation, changes in this way. So we have a22 x2 plus a23 x3 plus all the way up to a2n xn equals b2. And in this way, we now have a mechanism whereby we can go with m equations, m. Okay, so we have a m2 x2 plus a m3 x3 up to a mn xn equals b m. There are m right-hand sides because m equations. So all of these come down. So basically, now we have therefore here in this system we've got m equations. So that now we can clearly see what I was talking about. This is a very large system. Well, it can be, depending on the values of n and m. You can have as large a system as you like. And our objective is going to be, how do we solve these equations? How do we solve these large systems of equations? And it's going to be very interesting how we can use computers, in fact, to do that. So that's basically all I want to say about linear systems of equations in terms of their representation. Now let's look at some other points. One other thing I want to look at is homogeneous linear equations, or homogeneous linear systems of equations. Okay, what I mean by homogeneous linear systems is if B1 equals B2 equals B3 equals all the way up to Bm, all of these are 0. So in other words, that's a very unique situation, a very special situation where all the right-hand sides of the equation, all the right-hand sides of all the equations are in fact 0. Such a system is referred to as a homogeneous system. Now, we will look at, they have certain interesting properties, and we will look at those a little later on. But for the time being, we're just going to, I just want you to get an idea of the definition of homogeneous linear system.